Hello everyone. So this video is specifically for BC viewers. Okay, so this is for BC only. Okay, so AB does not need to know this, but this is a BC topic that is asked on the free response questions. And this topic deals with another method of approximation for differential equations. We learned about slope fields. Okay, that's a visual approximation. But this is, for BC only, this method is known as Euler's method. This is Euler's method. And Euler's method is a method for approximating like a point on the solution of the differential equation. If that solution cannot be found easily, you can use an approximation. And first we need to see what the intuition behind it is. So suppose you're given a differential equation with an initial condition. This is the solution. Okay, this is your solution, y equals f of x. Okay, and they give you this point. This point. Okay, let's call this x1, y1. Now, what do you do? Okay, so Euler's method basically abuses tangent lines, okay, in order to basically draw, in quotes, the curve. So let's see what I mean. So if I want to find out a good approximation for the curve, first what I would do is find the derivative at this point. Okay, so evaluate the derivative. Okay, the derivative will give you a tangent line. And usually Euler's method, you would pick a small step size, call it delta x or h. You can label it either way. Okay, a tiny step size. And what this does is it determines how far apart your x values are. So pretend is your step size h. You travel along the tangent line until you reach this point. Okay, and this is x2, y2. Now, this is not necessarily a tangent line, but you would draw another line with the same slope as a derivative at that point until you reach another step size, h, step length. And then you would draw another line up until the x-coordinate reaches another step length away. Then you would draw another line with the same slope as the derivative at this point. And see how we're sort of drawing the curve and it's very close to it, okay? We're not leaving the curve. Okay, so let's do a really good zoom in. This is our point. And let's say this is our step size. Okay, this is x1, y1. Okay? And dy dx says a function of x and y. Okay? Okay, x plus is a function of x and y. Okay? Well, you would find a derivative at this one point. You're given this initial point. Okay, and you draw a line with the same slope as the derivative at that point. So basically it becomes a tangent line until you reach this point. And the reason why it's this point is that this is x1 plus h. Okay, this x coordinates x1 plus h is a step length away. That's what I like to call it. A step length away. And now what do you do? Well, you would evaluate the derivative again at this point. Okay, let's call this x2 comma y2. Okay, you would evaluate this derivative again. Okay, so if this was a function, okay, where you put x and y in it, okay? Okay, so this means a function where you put an x value and where you put in a y value. If you were to do x, you want to draw a line with slope x2 comma y2, or basically the derivative evaluated at these 2 points. And you repeat the entire process until you reach a step length away. And then you draw a line with slope f of x3 comma y3, or basically the derivative evaluated at x3 and y3. Okay, and you keep on going until you reach your desired point, and that will be your approximation. Okay, so how would you express all of this in terms of x1 and of x1 and the term before it, xn minus 1, and h? So the x coordinate is pretty obvious. The y coordinate is not that obvious. Okay, so the y coordinate is, the change in y coordinate is y n minus 1 plus something. What's this ratio over here? Well, this is the slope of a line. It's the change in y over the change in x. Okay? So what you would do is, if f of x comma y is x1 comma y1 is your slope, okay, and let's call this b equals over h equals f of x1 comma y1. Seems confusing, but again, it's literally what slope is. Then you would multiply each side by h. Okay, so this is b. You're increasing your y coordinate by b. And now you could replace this with b equals h times the derivative evaluated at x1 comma y1. That's literally what Euler's method is all about. Using tiny little tangent lines with a given step size in order to approximate a point, an endpoint right over here. And if you have a small step size, it gets you a really good approximation. Okay, so let's apply it. So let y equal f of x be the particular solution to dy dx equals 2x plus y, where f of 1 equals 2. Use Euler's method. With step size h equals 0.25 to approximate f of 2. Okay, so how do you start this? So our x1, we have our initial point, 1, 2. Okay? So what's dy dx at 1 comma 2? Well, dy dx at 1 comma 2 equals 2 times 1 is 2 plus 2 is 4. Okay, and our step size is 0.25. So 0.2 will be 1.25 x plus our step size, comma, so it's literally following a formula, a recursive formula, okay? Yn equals yn minus 1 plus our step size times this derivative. Okay, so y2 equals 2 plus 0.25 times 4. Okay, and 0.25 times 4 is 1. Okay, so we have 2 plus 1 is 3. Now let's look at 1.50. What's the y value at this point? So now we have 3 plus, now we have to look at the derivative at 1.25 comma 3. Okay? Now this 1.25 is 2.50. 2 times 1.25 is 2.50 plus our y value 3, and that gets us 5.50. So you have to evaluate 0.25 times 5.50. Okay, and just to save time, we use a calculator on this. On the AP exam, they might give you a larger step size, so it's more computationally friendly, or this will be a calculator section question. Okay, so that gets us 4.375. Now for 1.75, our next x value, dy dx at our previous point is 1.50 plus 4.375, which is 7.375. So y4 equals 4.375 plus 0.25 times 7.375. Yes? Now what does that get you? What does that get you? We have 4.375 plus 0.25 times 0.25, and that gets us 6.219. We're going to go only to the thousands. And now at 2, finally, at 2 we have 6.219 plus 0.25 times the dy dx evaluated at this point. Okay, so 2 times 1.75 plus 6.219, that gets you 9.719. Now that gets you our approximation. 8.648. And now you can see that f of 2 is approximately 8.648. So there's nothing really confusing about it, okay? You're literally applying a formula repeatedly until you get to your desired x value. And the value of y you get is your approximation. So I know this is a confusing topic. It confused me when I first learned it. But if you remember the formula and apply it repeatedly, then you should be able to do fine on Euler's method questions. Remember, this is for BC only, so AB students, don't worry about this at all, okay? So thanks for watching. Make sure to leave a comment and like this video. Pass this video on to your friends and subscribe if you really like our content and would want more. Thanks for watching.